I'm going to talk about putting the pieces together to address the needs of applications. In our case, we're talking primarily about addressing the needs of DOE applications. Why did I add the caveat of one perspective? Well, depending on what your goals are and what the specific needs of the applications are, how you want to do it and how you address it is going to vary some. So I'm not going to pretend that I can cover all the possibilities here, but I'll give you a perspective on pulling it together. So what do I need to do to do that reasonably, if you will? I need to understand what functionalities they wish that we can provide for them, or if you will, jointly provide to some user community. Determine what components, what pieces of capabilities we need to bring together, and then also understand constraints. This is often overlooked in this process, and the constraints can be technical, they can be somewhat political, if you will, or for lack of a better term, political. But you need to consider them. So what functionalities are provided? For the examples that will be included in this presentation, we're going to be integrating tools to be able to support parallel unstructured, unstructured adaptive mesh-based simulations. The tools we're going to bring together are typically various FASTMath unstructured meshing tools and analysis codes, the solvers, the UQ technologies, optimization tools in situ. What I'll talk about here will be primarily using solvers, dynamic load balancing capabilities, and the meshing tools. And obviously we need the applications analysis components with respect to their physics and math models. They always will bring at least that much. What are the constraints? Well, when you're working with the applications people, they have to get work done. They have to advance their application. You can't, so coming in and saying, I've got a better idea, give me 5 years and I'll give you a code that starts doing something, doesn't work when we're working with applications. They need things faster than that. If they have an existing tool, which is often the case, they're going to expect you to build on that in one form or another. It may not be the optimal approach for the long run, but again, the first constraint of they have to continue to make advances really requires that you take advantage of what's already there. You can't just scrap it. Right, so what are the approach taken when there's an existing code? We provide mechanisms to integrate the needed tools with their code with as little modification as possible. We work directly with the applications people to gain their trust and to gain understanding of their application, because that's what's going to be necessary to take steps past that. And then incrementally, we typically evolve the tools together every once in a while, making a rather large change. So if the analysis code is found to be deficient, if they don't already have the analysis code, that is, you change the starting point, then you can do other things. So for example, today we heard about codes like MFEN in some detail, or Albany, or other finite element codes, or other, in our case, unstructured meshing codes. If they don't have a code, you can bring that to bear, or if they have a code that is obviously not going to be extendable, and I'll give an example of that type in a couple of minutes. But you need to overcome all the deficiencies, maintain compatibility with moving forward, and you have to demonstrate capability pretty quickly, and then support the real physics. It's often easy in a framework to demonstrate applications that look very promising, but when you get the real physics with the real material parameters and everything else, all of a sudden the problems get a lot harder to solve. Right? So what are the tools that we're going to be putting together in many of these cases? In the examples I'll be showing, we're going to be using the unstructured mesh infrastructure to bring in and support the direct interactions with the large-scale parallel meshes. We're going to be using dynamic load balancing procedures based on Zoltan and or ENGPAR, typically the two in combination. In terms of the analysis codes, we've already seen those, but there'll be MFEM examples and other examples here, but primarily MFEM. And in terms of the matrix systems, we haven't emphasized that. It has been mentioned, but all these codes we're talking about are using the various FASTMath equation solvers, and many of the applications we're working with now are more heavily using the optimization techniques such as tau that you just heard about, and the UQ techniques such as Dakota and UQTK, which you didn't hear about today. They will probably get their chance at next year's meeting when we cover other aspects of FASTMath. Right, so in this, typically when people are coming to work with the particular group that I'm heading up, it's because they have complex geometry problems and they're going to need to be able to deal with the meshing with that. So we often start off very early in the process of where you're going to get your geometry definition in terms of possibly CAD model, image data, combinations of those or other sources of data, and then how are we going to be able to automatically generate them either with open source codes such as GMesh or commercial codes or whatever combinations you want. What we're looking for in those codes is the ability, though, to work directly from the original geometry data. If you've got to spend months manipulating the geometry to be able to make the mesh, you really you're not going to make the applications people happy, if you will. You really want to be fully automatic and parallel in the mesh generation process, because again, that's very tedious to do otherwise. And once you do that, you have to provide capabilities to support the fields and manipulate the fields as necessary. So and as well as they may desire custom user interfaces. So what are the approaches we take for doing this? Because there's multiple options, and depending on the needs, we take different options. So in some cases, they're looking for us to put together very specific tools to support their specific meshing needs. In other cases, when they have an analysis code already in place, then they'll typically have us start off with a file-based integration in which we will do that using data streams and APIs behind the streams. They won't know about it, or behind the scene. They won't necessarily know about that, but we're preparing ourselves for what they're going to ask for next, which will be in-memory integration techniques. Now, in some cases, their infrastructure is simply not sufficient to meet all the needs in the long run, and we will refactor major portions of their code, but keep much of the physics of their existing code. And we'll mention two examples of that type. And then there's the directly building on top of a FASTMath analysis code. I'm going to just mention in 2 slides example of meshing capabilities developed, and one where it's both the meshing capabilities as well as directly building on MFEM to meet the simulation needs in that. Cameron is going to cover the fact that while we need to do better than file-based integration, he's going to describe to you a bit about how we do the in-memory integration and mention a couple of examples of replacing the infrastructure and why we needed to do that for existing analysis codes, but we didn't really want to rewrite all their physics, so we're doing that with trying to keep those portions as intact as possible. Right, so we do a fair amount of work with fusion applications. They have very specific meshing needs in terms of having field-following meshes in both 2D and 3D. They like the fact that in addition to giving them these mesh generation capabilities, we can do it in a GUI, giving them a GUI to go along with that. So we've developed specific tools for Tokamak types of applications. Now, a more challenging application, which we did talk about a little bit earlier, is the RF calculations for the fusion reactors, in which you've got to deal with a very complex geometry in terms of these antennas, coupled with the geometry of the reactor, the Tokamak device itself, with the fact that we're going to have meshes that need to obey certain surfaces that are defined from extracted physics from a particular sets of procedures, as well as a mesh for that was used for the interior core, right? And in this, we've coupled that together with the geometry construction procedures that Cameron showed you a quick demonstration of the defeaturing and that, and the parallel meshing, as well as on the analysis side, they originally had a set of capabilities in a particular code that it was clear was not a code that was going to be extendable to the 100 million degrees of freedom plus problems that they wished to solve, so that they made a decision to work with MFEM because of the ability of MFEM to be quickly extended to deal with their types of code. So we're now developing a complete workflow with them, combining a number of their tools with a number of the FASTMath tools. And at this point, I'm going to let Cameron take over.
So we put together these flow charts of the various components interacting to characterize the standard interactions and the differences between the applications that we've put together these workflows for. They all have similarities, but there's subtle differences between them. But the bottom line is that there's information being passed between these components that have different requirements, different sort of sizes and periodicity, or how often, or frequency, how often the transfers have to occur. So in the following slides, we'll look at how we support these information transfers, and in general how they can be supported. And we just note, as Mark said earlier, that most of these application workflows use some piece of FASTMath software from the catalog. So to support these information transfers, you can drive things from a top level with something that would look like a main. This gives you some advantages in the sense that if you have sufficient abstraction, you can quickly switch out your change components or the implementation of the APIs that drive these top-level interactions. You can also use the right level of abstraction for the information that's being coupled. Now, again, this is highly dependent on the implementation of the components and the workflow being set up, but at least gives you a better opportunity to expose it. Also, it's nice to set up these high-level jars because you can expose sort of the overall flow in one place, and the concepts match up with the code, at least in some sense. So the challenges for doing this are many, but first and foremost, you want to get away from file I/O. We saw in the morning talk that data movement on the next generation and current generation systems is very expensive. Computation's free. So anything we can do there is going to be beneficial for the efficiency of your workflow or your application. If we're going to do something like this, we're going to introduce additional memory bookkeeping or management that has to be added. We also have to be very careful or very cognizant of the coupling method that we choose for the information transfer. And this is, again, dependent on the components being coupled together. As we're passing information, we have to be careful about the balance of work to the various processes. And different components have different requirements for how much, for the data that they can efficiently compute on, and it's, so a solver versus a mesh adaptation tool, and so on. And lastly, knowing when you need to just simply rewrite and not necessarily just try to hook things together. So as I already mentioned, the I/O will dominate power consumption, so how can we eliminate it? Using APIs and data streams, we can keep the data local to the process. You saw Zanio's sockets with his visualization GLViz tool. So the data streams are much the same in that sense, as that you can set up a handful of APIs and you can basically pipe data between two components without really making deep changes to their data structures or the interfaces to them. So we would classify that typically as a bulk transfer. There's a large set of data being passed, and you can do that again with the streams, or you can use APIs if that level of data structure manipulation is exposed. So with this, if you have an old code, you may have to do some work on interface definition, and there's going to be memory management, especially if you have to refactor the code a bit to control its execution in a finer granularity than what was previously exposed. So essentially the opposite of that is doing atomic transfers, where you're passing small bits of information between the components. So here, if you think of this being, like all the mesh data on a process, the atomic transfer could be the data associated with a node or a couple of nodes, or patch or cavity of nodes. But this really only is possible if the component is providing a rich set of APIs, has data structures that support the right granularity of access to them, and so on. And if you're going to do this, the big challenge is you have to really understand the implementation. And, good API goes a long way, but you still have to understand the details of that component. What this can also get you is a memory savings, because you can start reusing components on both sides as you have access to the lower level queries. And again, the components you're working with are the ones that are going to determine how well this all goes together. So a quick example of two sort of extremes. You have the Albany code, which is something of a trilunos demonstration multi-physics framework, is using template metaprogramming from C++. So we can use the bulk APIs to transfer data back and forth between what are unstructured mesh data structures and their mesh discretization structures. And for Pasta, it's a older Fortran 7790 code, very little interfaces to the internal data structures, and we have an existing file I/O mechanism that has been in place for about a decade. So there we can use the streams to quickly introduce components, get rid of the file I/O bottleneck, and also maintain backward compatibility, as we indicated earlier. So again, balancing the workload is critical. You're having components interact sort of live versus potentially just passing files between different job executions. So keeping the workload balanced at all times is important, and we can do so using a combination of the FASTMath packages. Parmetis isn't necessarily a FASTMath package, but Zoltan can drive it. And that can be a high-quality route to get either a dynamic load balancing or a static partitioning of your data if you're just increasing part count. And then you can follow it up with R and partition improvement tools, engpar or Parma, depending on what data you have. So we just looked at some examples of how we're going to stitch components together using existing code bases, but now we have the last example where we find that there's a deficiency, or we find there's a sort of a need for another level of work. So for the M3DC1 code, we found that there was a deficient mesh data structure to really do what we wanted. So we introduced Pumi. We used that data structure as the sole mesh data structure, and we produced the results we needed to. Then for XGC, which Mark has shown earlier, we had to sort of flip the parallelism and have the mesh be the driving distribution and have the particles sort of go along with it. Obviously, we're very sensitive to the particles because they are the dominant computation, but still we're using the mesh as the main distributed work unit. So in closing, the FASTMath components are designed for efficient integration into application codes. We provide the components, We provide the multiple ways you can interact with them, from the simplest command line stuff to the deepest sort of atomic transfers that I mentioned earlier. And we provide the support for you to use these components via mailing lists, Slacks, Gitters, Jiras, Confluences, so on, so on, so on, all the way to you're sitting with the developer of the specific package and you're working together to get your software stack up. And again, we provided our perspective on putting it all together, so it's very biased from the unstructured meshing angle. And we emphasize you should talk to the other FASTMath team members tonight in the one-on-one speed dating sessions to understand what their perspective is on putting it all together. So, thank you.